Okay, so let's officially start. Hello, everyone. Welcome to episode 64 of Warsaw Quantum Computing Group Meetups. My name is Pavel, and I will be the moderator of this event. And today we have pleasure to host our great speaker, Maria Violaris, and she will give a talk about developments in superconducting erasure qubits for hardware-efficient quantum error correction. Before we start, I would like to announce that this meeting is recorded, as you can see, and also if you have any questions, if there are some, let's say, quick questions to clarify something, you can raise your hand and we can try to interrupt and answer on the fly. If there are some more general questions, there will be also a Q&A session at the end, so you can also post your questions on the chat and we'll try to ask them at the end, of course. Yes, before we start, I would like to thank our strategic partners for supporting us and making this event happen. Sonovero R&D, Onyx Alpha, Cogit, QuantumZ.io, and FinQubit. And we'd also like to thank our honorary partners for helping us in advertising this event. Okay, so now I will stop sharing my slides. And Maria, if you are ready, you can start sharing yours.
Yeah.
So first of all, thanks for accepting our invitation. It's our pleasure to have you with us and hear again about the quantum error correction.
Yeah, thanks for inviting me. It's always fun to talk. And yeah, this is a cool group. I've seen the list of past talks is lots of interesting speakers and topics. Yeah, cool. So I can get started.
Mm-hmm. Yes.
Great. And you can see my screen okay with the slides.
Yes.
Yeah,
Yes, I can see your slides. Mm-hmm.
great.
Perfect.
Cool. So hi everyone. Thanks for joining this talk. So I'm going to be talking about some aspects of quantum error correction that I've been looking into recently as I started working at Oxford Quantum Circuits, which is a scale-up building. It's a spin-out from the University of Oxford, building superconducting quantum computers. And I'm part of the theory team of the company, and part of my work is working on quantum error correction. So I thought it would be cool to tell you about some of the interesting things that I've been looking into recently. And this has been kind of, there have been lots of very recent developments on this type of error correction and the ideas behind it. So I think hopefully you'll find it interesting. And just to briefly introduce what my background is, I recently finished my PhD at the University of Oxford, which was in the foundations of quantum information and quantum thermodynamics. I also previously worked at IBM Quantum alongside my PhD, part-time doing quantum education work. And before that, I did an internship with Riverlane, the quantum software startup, and now work at WQCG. And I do lots of outreach and engagement, and also have my own content with a video podcast if you are interested in checking that out. And so what I do now is a lot of hybrid things. So my role at Oxford Quantum Circuits is developer advocate, which is a hybrid of quantum error correction research and technical science communication, writing blogs like this one that I wrote end of last year. And I also am making content on my personal YouTube channel and the podcast, and I've got some ongoing foundational research from my kind of PhD work directions. So the outline of this talk, I'm gonna start with a bit of background about quantum error correction to get everyone up to speed on what it's all about and how it works, and get us all using the same terminology for the rest of the talk. And then I'm going to talk specifically about what erasure qubits are, which are the kind of core aspect of what I'm going to talk about today. I'll give an overview of some of the recent progress with both theory and experimental developments that has been happening in just the last couple of years, so very recent developments in this area. And with a focus on what's been happening in the superconducting qubit space and where the qubits being developed at OQC fit in with these developments. And then a kind of summary of the outlook and open problems at the end. So to start, what is quantum error correction? Well, probably this audience is familiar with the fact that quantum computers face the problem of noise with there are lots of different physical platforms for implementing qubits, but we have this problem of them having these unwanted interactions with the environment, causing errors. And when we have our nice, coherent state that's storing the quantum information for the computation that we want, and then we get this noise, it causes these qubits to then collapse so that they're fixed as 0, 1, they lose their nice superposition, and that destroys the computation. So it doesn't work anymore. And the solution to that is quantum error correction. So this is just a kind of visualization of how the quantum error correction process works. So the idea is that we normally have our physical qubits that we can imagine contain our data. So here you can imagine having 2 physical qubits with the data. And then you bring in a bunch of extra qubits, which we call ancillary qubits. And then what you do is encode the information from the physical qubits across onto these extra qubits to create logical qubits. So the physical qubit information is now stored abstractly as a logical qubit spread out across these extra qubits. And then you can do this strategic process of doing measurements for errors. So these measurements will tell you what the errors are. But importantly, you can do these measurements without actually collapsing the information that you care about. So you don't collapse the logical qubit state, but you still find out what errors happened to the physical qubits. And so you do these measurements to extract this information. You do a decoding step to actually figure out from your measurements what the errors actually are that physically happened on these qubits. And then you do a correction step based on that information to fix those. And then your logical qubits are protected information. And when you do quantum computing with quantum error correction, so with everything encoded in these logical qubits, then you have to figure out how to do your quantum gates on this logical level. So you have to figure out what physical operations on your physical qubits will implement the right logical operations on the logical qubits. And then you have to constantly be doing this cycle as you do your computation of measuring for errors, decoding, and correcting. So this kind of keeps happening as you do your computation. And then at the very end, you actually do want to measure your data qubits, your logical data. So you measure that, and then you get some outcomes, and then you kind of do your final decoding to figure out what your measurements are actually telling you. And in terms of the physical level of what happened to the data. So that's the kind of flow of how a quantum error correction process works. And the aim is so just doing this process of quantum error correction isn't enough for having a quantum computer on a large scale that's robust to errors. You need to achieve fault tolerance. So what that means is that as you increase the size of the code that you're using to encode this data information, your logical error from your logical qubits is decreasing. So this might not necessarily be the case because you can imagine you're bringing in more noisy qubits when you're doing a bigger code. So it might not actually help your logical error go lower because you might be bringing in more error than you're taking out with the code. So fault tolerance is really this point where you actually are getting a benefit from increasing the code size, and you can make that logical error go down. And that is reached when there's a theorem, the threshold theorem, which says that if you can get your physical error on these data qubits to be below a specific value, then you can achieve fault tolerance. So that's a really important point to reach, is this threshold where you can say, okay, if I build my physical qubits, get the error below this amount, then we can just scale up with all those physical qubits and get the logical error down. And so that was the kind of broad idea of quantum error correction. And then more specifically, there's a bunch of different proposals and ways to actually try and do it. So different quantum error correcting codes have different properties. They have different advantages and disadvantages. And some are kind of tailored for specific hardware platforms as well. So the most kind of popular and established one is the surface code. So this is the one that Google have gone for in recent demonstrations and in general in the past. And that one is kind of the most fleshed out in terms of people have worked out how to do logical operators using the surface code, and it's kind of very nice for superconducting qubits because you just need kind of nearest neighbor interactions between the qubits. So there's lots of nice properties of this one. There's others that have been kind of becoming more popular in recent years because there's been some interesting developments with them. For example, QLDPC codes have promise of being able to use fewer physical qubits than you need for the surface code in order to get the low error rates. So IBM have been looking at an example of that. And there's many others with their own kind of interesting features. And in quantum error correction in general, there's been a lot of recent developments. So especially the last few years, there's been this kind of increase in experimental demonstrations and actually showing that this works, that the theory of quantum error correction actually checks out, which is really cool. So one that kind of surprised the community, I think, was this result in December 2023 about a logical quantum processor based on neutral atoms. And this was cool because they created like a bunch of logical qubits and showed logical operations on a lot of qubits. So that was that kind of felt like a step up where it was like, oh, we can actually do this level of things with logical qubits. And then there was this cool theory result from IBM kind of relating to this QLDPC code that I mentioned, of showing that it can have some really nice properties in terms of saving qubits. There have been some cool results on ion traps as well. Quantinuum and Microsoft, for example, has done some experiments with logical qubits. And the recent one that caused lots of discussion was Google's announcement of their Willow chip, which kind of brings together all the pieces for quantum error correction to work on kind of a single surface code qubit. So that was a cool result, and I was inspired to make a reaction video for it on my YouTube channel if you're interested, because it was getting so much interest from the broader world into quantum computing. So yeah, there's been a lot happening. And a lot more that I've not mentioned here, but these are some that kind of arose in the community. So that was the kind of background context on quantum error correction and developments. So now I want to talk about something kind of more specific and recent, with kind of recent developments. So in particular, erasure qubits. So I'll introduce kind of what an erasure qubit is and then how this is kind of relevant for quantum error correction and what's been happening with these. And so the general idea of erasure qubits. So I'll kind of give an example with this diagram. So the idea is that you can imagine encoding using two physical qubits to encode one logical state. So doing like a 2-qubit code. So the idea is that you have these 4 possible states of your 2 physical qubits. You've got 0, 0, 1, 0, 0, 1, 1, 1. And what you do is you have your 0 logical be 1, 0, your 1 logical is 0, 1. And you use these as your computational states. So you want to manipulate your 0 logical and 1 logical. Now, if say you encode this 2-qubit code with superconductors, the kind of dominant error is that you'll have it de-exciting and going down to the ground state. So you'll get the state going from 1, 0 to 0, 0, or from 0, 1 to 0, 0. And the idea here is that if you get this kind of error, where you go from your logical space of 0 logical and 1 logical down to this 0, 0, it's actually outside of the space that you're working in. It's outside of the logical space, outside of the computational subspace. And the reason this is cool is because you can then detect that this error has happened. And in principle, you can do checks to see if this kind of error moving outside of the computational space has happened without actually collapsing the logical state, because the error is outside of the computational state rather than within it. And so that's the kind of trick, that if you can detect the error from that's been happening outside it, you don't need to actually collapse the logical state. And this is cool because it can then give you information about the location of an error that you can't get with a normal error correction if you're just doing the surface code with physical qubits, for example. So, and I'll explain this in more detail to explain kind of how this actually works, but that's the kind of idea of using this 2-qubit code. And this way of doing it in particular is called a dual rail qubit, this kind of form of encoding. So this is the kind of key point that I will explain in more detail, but it's that these errors are taking you from somewhere inside the subspace to out of it, and you can detect that without collapsing the computational information that we care about. So the process, the kind of overall idea is to do erasure conversion. So what we want to do is make these erasure errors where you're going outside of the computational space to be the most dominant ones, do checks so that you can detect them, and then use these kind of 2-qubit encodings as your physical qubits within another code. For example, the surface code I mentioned before, normally you'd encode across a bunch of physical qubits. You can imagine replacing each of them with these dual rail qubits, and then you kind of have this what's called concatenation, where you kind of combine one code within another code. So within our top level surface code, we have these 2-qubit codes, and we do checks on them to detect errors happening. And then we have location information of where the errors are happening, which can help us do better than a usual surface code. So the kind of motivation is if we can engineer the noise of the physical qubits that you're using for the surface code to be these erasure errors that are escaping the computational subspace, then you can add in this information about location of where the errors happened. And this turns out to have some big potential savings for the errors that you can withstand of these physical qubits. So I'll kind of outline the workflow of how this would work, and then I'll kind of zoom in on some specific examples with the surface code to kind of show really what I mean here. So first, what you do is do an erasure check. So this is checking if an error has happened without collapsing that logical, 0 logical, 1 logical state. And it'll tell you the location of an error if it comes up, because you do this for each qubit, so you know which qubit has this error. And then what you do is you convert this into an error that is actually in the computational subspace. So you take your errored qubit, you apply an operation to reset it, and what this reset does is it pushes it back into the computational subspace. So usually we'll just reset it back into some random mixed state within the computational subspace. So now it's back in that subspace, but it's got an error because it's just in a random state. It's not in the state it was in originally. And so it's become the kind of usual kind of error that we're dealing with, which is errors within the computational subspace. And then what you do is your kind of usual quantum error correction protocol that we saw at the beginning of doing these syndrome measurements, these measurements to extract what the error is. And the information from those measurements will tell you what type of error you have. Like, is it a bit flip or a phase flip? So in general, errors can be decomposed into these two types when they're happening within the computational subspace there. The bit flip errors are when there's an X gate thrown accidentally or unwantedly, and then the phase flip are when there's like a Z gate thrown on that you don't want. And so you identify the error type using this kind of usual quantum error correction process. But this is where the advantage of the erasure qubits comes in, is when you're now trying to decode to figure out what errors actually happened, you can use this information about what location the errors happened that you got from the erasure checks, and then use this to correct a lot more errors than you could without that location information. Because usually, if you didn't have that, you'd have to try and guess the location based on these measurement outcomes from the usual quantum error correction cycle. But here you're getting that information from these checks is telling you where the errors happened. And so this has been kind of explored for the surface code in particular, since it's the kind of standard fleshed out example of a good code for quantum error correction. And if you make this simplification of making these modeling the syndrome measurements, the measurements of what the errors are, as being ideal, so as not having errors, then it's been shown that having a surface code plus information about the location of the errors, which is what you get from the erasure checks, takes your threshold to be very high. So 50% is a really high threshold. So this means that you can get fault tolerance if the errors on the physical qubits are up to 50%. And obviously there is a big simplification in this case. So this isn't the kind of realistic threshold, but it kind of shows how it can lead to it being very large. And this is actually it's actually a fundamental bound on the threshold for a surface code, which is imposed by the no cloning theorem, the theorem that you can't copy an unknown quantum state. So that's quite cool that you can really get up to this fundamental limit of what your threshold can be. So this is kind of what excited people about erasure qubits, is that they provide this pathway to getting this location information, which unlocks these higher thresholds. So to go more specific into a surface code example, this is kind of the layout of a distance 2 surface code. So what this means is that we've got 4 data qubits. These are the D1, D2, D3, D4. And then we have 3 ancilla qubits. So these are our extra qubits. And we use one of them to check for X errors on D1 and D3. This one checks for Z errors on one of these 4 qubits. And this one checks for X errors on these 2 qubits. And let's say an error happens on one of these 4 physical qubits that are storing our data. And this ancilla flags, so this tells us that there was a Z error on one of these 4 qubits. But it doesn't tell us which qubit had the error. So with a D equals 2, with a distance 2 surface code, usually, so without the location information, all you can do is detect whether an error happened. So you can know that an error happened from looking at one of these 3 ancillas going off. But you can't actually figure out where the error happened. So you can't correct an error. But when you add in location information, so let's say we did an erasure check and we saw that the error happened on this qubit, then you know the type of error because this ancilla went off, so we know that it's a Z error, and you know where it happened, so you can actually do correction. So with location information, you can turn a code from a detecting code to a correcting code, and more generally, you can improve the properties of your code. So that's the kind of idea of how an erasure qubit works. And now I want to kind of zoom out a bit to give a bit of context on how did erasure qubits get involved in quantum error correction? Kind of what's been happening in the field with these erasure qubits? Like, have they just popped up now? And so here's some insight on that. So there's a kind of original paper proposing these erasure channels as being interesting for error correction back in the 1990s. So the idea was around from then, and that was kind of showing that there's some interesting savings in terms of the threshold having these interesting properties. And then this dual rail qubit that I mentioned, this kind of dual rail encoding has been, since the 2000s, there were these like proposals showing that you can build a kind of mapping out how you'd build a fault-tolerant quantum computer using photonics and do quantum error correction in general using photonics. And in that context, dual rail encoding is really natural. And the reason for that is that with a photon, you you have, so you need to, in general, when you pick a qubit, you need to pick what your degrees of freedom are that you're going to encode your qubit on. And with a photon, you've got a lot of options. You could use the polarization of the photon as your 0 and 1. So one polarization is 0, the other is 1. You could use the pathway of the photon as the 0 and 1. So when you send it through a B splitter and it goes down two paths, one is 0 and the other is 1. You can even use the presence of the photon as a 0 and 1. So the photon being there is your 1, and the photon not being there, the vacuum, is your 0. And that's not a great idea in the sense that it's difficult to control the presence and absence of a photon as a qubit for computation, but you can use it as like an extra piece of information alongside having one of the other encodings for your qubit. So let's say you use polarization to do your photon qubit, and then you use your presence or absence of that photon as a kind of extra degree of freedom. And in that case, you kind of have these erasure qubits coming out naturally because if a photon disappears, then you kind of naturally figure out that you detect that there was an error just by checking whether the photon is there or not. So it was kind of a natural thing in the context of that hardware specifically. And then there's also been work on kind of engineering qubits for savings in quantum error correction with in a different approach of biased noise. So the idea is if you can engineer your qubit to have a specific type of noise, then you can save a lot on quantum error correction. So one example is if you try and engineer your qubit so it only has X errors and not Z errors, then you don't need a full-on surface code to correct it. You can use a much simpler code to correct it. So that's kind of getting into this idea of engineering your noise to be optimal for quantum error correction. But it's only a lot more recently that this idea of kind of erasure qubits gained popularity. So it's just been in the last few years, kind of from 2022, where there have been proposals for doing this erasure conversion process using neutral atoms, trapped ions, and superconducting qubits, and some experimental demos kind of following those proposals on then showing how this can actually work. And last year there was a bunch of work on kind of optimizations of working with these erasure qubits as well from a kind of theory and simulation perspective, trying to figure out what's the best way of using them. And this kind of theme is part of something broader. So there's this idea of a design principle for hardware efficient quantum error correction, where the idea is to engineer the noise and the code together so that you kind of really optimize them both. So erasure qubits is kind of trying to do that in the sense of engineer your noise to be erasures and then get that to fit together with this code on top, the surface code, and have them you then need far fewer. If you've got a higher threshold, then you could need fewer, have a much easier time using your code. So I like this Escher drawing as a depiction of this code development of the noise and the code engineering working together. So now I want to focus a bit specifically on superconducting qubits, because there's some interesting motivations for why they're particularly interesting with superconductors. So with superconductors, there are two main kind of noise sources for a superconducting qubit. One of them is amplitude damping. So this is when your qubit goes from its excited one state down to its ground state. And the other is dephasing. So this is where you get a phase between your 0 and 1. So in terms of usual quantum error correction errors on the kind of more abstract level, the amplitude damping is your bit flips, and the dephasing is your phase flips. So bit flips, you go 0, 1, 1 to 0. Phase flips, you add a phase to the one amplitude. Now, for dephasing errors, there's known techniques for reducing those and bringing them much lower. For example, dynamical decoupling is one of these techniques. So that puts amplitude damping as the kind of bottleneck for reducing physical errors on superconducting qubits. And so the cool thing about using erasure qubits is that if you convert the amplitude damping errors to erasures, then you can make that much smaller. And then you could even get to a stage where it's actually your dephasing errors that are now the bottleneck. And overall, you've made your physical error significantly smaller. And so you're kind of not being bottlenecked by your amplitude damping anymore. And this can help reach the threshold for fault tolerance, which is, yeah, the idea is that if you can use tricks to get that error down low enough, and then you can reach that point where you can start scaling up and reach the fault tolerant threshold. But there's also another aspect that it's useful for NISQ as well. So near-term intermediate scale quantum computers. So this is the kind of the era before we have a fully error-corrected quantum computer. Converting, doing like detection of erasure qubits is useful for that as well, because you can use it as an error mitigating technique. So it's something that you can kind of start using now essentially, and then build up to use it for achieving that threshold in the future. So expanding a bit on how you actually do this with superconductors, there was a nice paper kind of proposing different ways that you could do it on superconductors, published in 2023. One of them being this dual rail qubits, one that I kind of explained before, but another being to actually use a qubit, so a 3-level system. So these dual rail qubits aren't the only way that you can engineer this kind of noise. There's other ways of doing it as well. So you can get creative with how to build an erasure qubit. And so these are some of the ones that people are actually developing. So there's teams kind of based at Yale and the company Quantum Circuits that are developing them based on cavity QED. So they had some interesting work last year. And AWS have been working on a kind of coupled transmons approach. So the idea is that you combine, you couple 2 qubits together to make the dual rail qubit, and you have this ancilla to check it as well. And then the qubit that's being developed at OQC is the daimon, and this is a kind of depiction of that. And I'll expand a little bit on what's happening with the daimon and how it works and what's happening here at OQC. So the motivation is that with the approach of kind of taking 2 physical qubits and then coupling them to do the two qubits in one, to do the encoding. That's this coupled transmons approach. You need kind of two transmons to be in your system. And the idea with the daimon is to kind of wrap up those two qubits in one and have the footprint of one qubit. And also ideally not have a kind of extra hardware for doing the check on the qubit as well. So removing the ancilla from the footprint as well. And so the way this works is this is the kind of depiction of the usual qubit at OQC, the coaxmon, which has these kind of two superconducting islands. And then the modification with the daimon is that you instead have three islands, and the kind of core part of superconducting qubits is the Josephson junction. And so instead of one, you now have two. And what this lets you do is kind of excite two modes of the same physical hardware, and you can use those two modes as the dual rail encoding instead of having to add another qubit. And so the with the kind of current daimon that's been developed, there's a nice blog by one of the quantum engineers at OQC, James Wills, on the website, which goes into more detail, but the idea is that you kind of have this footprint of one qubit. You don't have the an extra ancilla to do detection, and the team's been doing some experiments doing the kind of error detection to show that you can actually do a detection of whether an erasure error has happened or not. So it's a specific type, so it's called end of line, which means that it's not the check that actually lets you not collapse your state. It's a check that tells you your erasure error, but isn't preserving the state. So you'd need the preservation part to do quantum error correction. But for now, it's the first step of doing error detection, which is this part that can be used as a kind of mitigation technique in the near future. It is a step on the way to the mid-circuit version, which would actually preserve the computational state. So I took these from James's blog, which are some fun figures showing the results of doing this process to kind of do the error detection, and it these are kind of showing the measurements of the different possible states, and then so it's this 0, 0 is the one with the erasure error, 0, 1 is the logical 0, and 1, 0 is the logical 1. So you can kind of detect which of those three you have. And then you can see this kind of Rabi oscillation arising when you correct for, when you take into account your error detection. And so you can kind of get this big improvement on the error. So that's yeah, kind of coming to the end of the talk. I just wanted to wrap up with some kind of outlook and open problems. So one of them is I kind of focused on the surface code when explaining the idea behind erasure qubits. But it's actually an open question of what the best code might be for erasure qubits. So people are asking, is it particularly good for one kind of code, or does it just kind of help all codes similarly, or is there some that are kind of optimal ones for erasure qubits? So that's an open question that on the theory side is an interesting one that people are looking into at the moment. Another area is that there's lots of room for optimization. So I mentioned that last year, 2024, there was a bunch of work on kind of various simulations and work on optimizations of like, how do you schedule your checks of the erasure qubits? What kind of reset protocols you do to put them back into the computational subspace, various trade-offs with if your checks have errors, then how you account for those. There's also ideas for a kind of hybrid where you could have a mixture of normal qubits and these dual rail qubits, and maybe that's optimal. And there's questions around the best way of doing decoding. So this figuring out how you account for this location information in your decoder in the best way. And in terms of kind of outlook, I expect that we'll have this kind of co-design process continuing of kind of working on the hardware innovations of the noise, designing the noise, trying to understand the noise, and thinking about that in kind of together with thinking about the code and the properties of the code and finding the best way of getting those to work together. And so, yeah, work on this has been happening kind of, yeah, like I mentioned, in the very recent last few years. So I kind of expect that we'll have more theory and hardware developments in the coming ones as well on this area. So just to summarize, I have some footsteps of our progress through the summary. So I've talked about erasure qubits, which are a kind of cool way of doing quantum error correction, where the idea is of having these engineering the dominant noise to be these erasures that are actually leaving the computational subspace. And this provides a realistic pathway to threshold with superconductors because it kind of increases the threshold of error to a point that's actually feasible, like realistic, when you think about kind of what a realistic amount of noise is to engineer the qubit to get to. So that's cool. And there's been lots of recent progress on theory and experiment on different platforms, neutral atoms, trapped ions, as well as superconducting. And there's different groups that are kind of trying different approaches with superconductors and innovating on those as well. And because this is quite a recent idea being explored, there's lots of kind of open space for iterating on this approach and optimizing on some of the aspects that I mentioned as well. So yeah, thanks for listening. I'm happy to take some questions, and I've also just put my socials and content details on here and the OQC details here. And just a note that if anyone here happens to be going to APS March meeting, there's a big group of us going with a lot of talks there as well. It's in Anaheim where Disneyland is. And this is the OQC team from a summer party last year before I joined. So yeah, thanks for listening. Happy to hear questions.
Great, thank you. Thanks, Maria. Thanks for a great presentation. And yes, we have some questions on the chat, so maybe I can start from these questions that have been already posted. So let's go. I will go back to the beginning. So there was a question about or whether this is recorded. Yes, so it's recorded. There was also a question if we can also share the slides. I'm not sure, Maria. Would you like to share the slides as well? There will be a recording available anyway, so maybe this
Uh-huh.
is sufficient. Okay, but there is a merit question. There's a question about references, but we can ask it about it later. There's a question from Mohammad Reza. Would moving toward cat qubits be considered a variant of the realization of this interconnected noise code engineering? So this is a question from Mohammad Reza. And Mohammad Reza, if you want, you can also try to unmute yourself and ask.
Um,
I'm not sure if you can see this question. Yes? Do we have Mohammad Reza with us? Maybe I can,
I
yes. Mm-hmm.
so I just maybe read off the comment if it's fine. Yeah. So, yeah, this is my question. Would moving toward cat qubits be considered a variant of the realization of this noise code engineering?
Yeah, 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 it would. So the kind of biased noise here was kind of this yeah, part of that was this idea of using cat qubits, so qubits with a specific kind of error of just X errors, for example, say. Um, and yeah, that's kind of a similar vein to this design principle of having the code and the noise engineered together. And yeah, there's been interesting work kind of combining these ideas from AWS, and their team had a paper on uh cat qubit cat qubits in hybrid with like transmons, and then I think they used an aspect of kind of erasure qubits there as well, because they're also looking at erasure qubits. And so yeah, there's ways to get those to work together as well.
Mhm.
Okay, so I have some other questions, but maybe you can, yeah, ask the others first, and then,
Muhammad
yeah.
Reza, I think this is fine, and you are already unmuted, so please go on and
So, okay, okay.
yeah.
So the others are, can you enumerate the ups and downs of different quantum correction codes? So you named some
Mhm.
surface codes, QC, yeah. So what are some?
Um, so uh yeah, so one example is that the surface code needs loads of physical qubits per logical qubit. So that's a kind of a problem in the sense of needing so many qubits. And so
Oh,
the nice thing about the QLDPC codes like this one that IBM are looking at is that you need far fewer number of qubits to to get the same amount of error correction. Um, but this QLDPC stuff is kind of a bit of a high risk, high reward
oh,
approach, because there's that has its own challenges. For example, the operations for doing logical operations haven't been worked out. And so we don't know if there's like
oh,
nice ways of doing that. Whereas on the surface code, there's really nice ways of doing logical operations that are already worked out. Um, and then there's also issues of connectivity. So this kind of approach that IBM look at, for example, needs long range connectivity between the qubits. So they have to kind of put more work into um, engineering that kind of more difficult type of hardware in order to implement
yeah.
this code, as opposed to the surface code that you can kind of use the more standard stuff that has already been demonstrated. So they're kind of yeah, the types of things that can be different.
Okay, thank you. For my last question, perhaps, is the process of discovering new codes principled at all? If so, what are some guidelines for discovering new codes?
Um, yeah, I'm not really sure how people
Hmm.
went about, say, discovering new codes. I guess a lot of the time it's kind of there's a level of modifying codes. So the surface code went through, there's lots of different versions of it that are kind of so it's been kind of evolving. So I guess that aspect can happen from kind of um yeah, I don't know, studying it, what maybe
Yeah.
um yeah, I don't know if people can maybe think of a particular property that they'd like a code to have and then look for something that has that, or at least a variation of a current code that has that.
Mhm.
But yeah, so
Yeah.
it's an
Okay.
interesting question.
Thank you very much.
Mhm. Good. We
Thanks.
have some further questions. Let's maybe ask the question from Venkat. Will erasure checks promote better state preparation schemes for topological codes?
I think they should do because of in general enabling quantum error correction with lower threshold, then the state preparation should also be made more feasible to do with low error, low logical error in that case. So it should be a kind of something that comes with doing the quantum error correction with higher threshold.
Okay, thanks. There is a question from Christian. Christian, would you like to unmute and ask? Because I see that you also posted a follow-up message. Maybe I can first read this question. Are there any efforts going on towards some micro-cooling solutions for superconducting chips that you can share? It's not fully related to the scope of this talk, I believe, but that was asked by Christian, so
Yeah, so I don't really work on the kind of infrastructure side or hardware side, but I think that at some point trying to scale up the fridges might become something that needs kind of innovation on the fridge side for space reasons. I don't think it's currently the bottleneck for people, but it yeah, I imagine in the future some people building fridges will innovate on that. But yeah, I don't have many ideas on that.
Probably, I'm sorry for a small interruption. Probably
Yes.
you can also try to use laser cooling to miniaturize certain things. I would guess, but I'm not expert on that. I would guess that you can try to do it as well.
That's kind of what happens with trapped ions. It's more that you use the lasers to get the control and the isolation. But with superconductors, you have to get your superconductor down to the superconducting temperatures, and then yeah, dilution refrigerators are the only way I'm aware of people kind of practically doing that.
Good, thank you. So Krzysztof, as you have already interrupted, maybe you can also ask your question because I see that you've also posted one.
Yes, I have a question. Are you aware of existence of some error correction codes for hybrid quantum systems like semiconductor quantum dots interacting with superconducting qubits or some other types of hybrid quantum systems? So do you know about existence of such error correction codes?
It's not something I know about. But I guess like on the abstract level, the error correcting code itself doesn't really distinguish between what the hardware is, apart from the fact that it would need to have the right connectivity for the code. And then I guess if different systems had different noise profiles, then that would complicate figuring out the thresholds and things. But yeah, I imagine you could apply the kind of at least the broad ideas from existing quantum error correction theory.
Well, I would say that I would expect different systems, quantum systems, to have quite different noise statistics. And actually, it's a question if, I mean, to because there are certain conservation of certain quantities, like total momentum, whatever. I mean, this conservation principles might serve as a kind of criteria for justification of existence of error or not. I don't know, but I'm just curious. Was there any attempt in such direction from error correction point of view to account error correction for different quantum systems? That's my kind of wondering, because I'm not expert, so that's why I'm asking about such possibility.
There's definitely work on different noise models. So that's a kind of big thing, is to try and make our theoretical models of the noise better, and that will be different for different types of hardware, even superconducting qubits implemented in different ways. But it'll be different for troptowns, different for neutral atoms, different for photons. And so yeah, so there's lots of work being done on trying to understand the noise better and model it better, and use that in simulations to be able to get better results, because yeah, often we make kind of big simplifications about how the noise is working and then come up with some theoretical results, but you kind of don't know if they'll actually work out that way without actually doing it on hardware that has the actual complex noise model.
Okay, thank you for the answer.
There is another interesting question coming back to erasure qubits. Can this approach, erasure qubits, be extended to distributed error correction like the locket codes? I'm not sure.
I'm not familiar with distributed error correction, so
Okay.
I'm not sure.
Okay, that's fine, no problem. There was a question from Michael. Michael, maybe you can also unmute and ask.
Yeah, so I mean, I found the presentation intriguing, but I feel like to really understand the concepts, I need to see a simulation, and ideally, I'd like to program my own simulation. So then I was wondering, are there any quantum error correction schemes that can be simulated in a standard circuit simulator? So I asked the question in the chat, and then I also asked an LLM on the side, and it said, well, no, you probably want to use Qiskit or Cirq, and it suggested some libraries for doing that. It also suggested that I start by simulating bit flip or phase flip errors and then later maybe depolarizing channels. But I wonder if there are other schemes that would be good to look at. Like today you were talking about the dual rail and erasure qubits. Is that sort of a more advanced scheme, or is that something that a beginner like me could maybe try to simulate?
I'd recommend, well, the simulator that's like the thing that that people use for quantum error correction specifically is called STIM. So this was created by Craig Gidney, the same guy that made Quark. And he kind of made it with the intention of being frustrated with error correction simulations being really cumbersome and long, and wanted to make like something that's much more efficient. And he developed STIM, which now saves loads of people loads of time when they're investigating quantum error correction. And yeah, I mean myself, I've kind of just started looking at it, so I'm not I don't have much insight on what it's like to use, but he's got some videos about it and like the code online with like examples, and yeah, so that's kind of what a good one for kind of, yeah, I guess hardcore error correction simulations is a good one for that. But I mean, you can do the kind of I guess more, yeah, depends what you want to do, because you could also do more exploratory examples with the other simulators like Quark, for example. If you say want to do a repetition code or a small surface code, like the example that I said, that you can probably kind of do that on the kind of quantum circuit level, but by figuring out what the circuit is for encoding and kind of manually put in some errors. But for a kind of proper simulation, probably something like STIM is best.
Okay. I just found a video tutorial about it and I put a link in the chat. Thank you very much.
Yeah.
Okay, thanks, Michael. I see two more questions. Maria, is it fine for you to answer two more? Okay. One
Yeah.
question from yes, one is from Ankit. It's not fully related to the talk, but let's see. Can we perform register-based quantum error correction like the repetition code autonomously with just reset and no readout?
I'm not familiar with that, so I'm
Okay.
I'm not sure.
That's fine, no worries. And the last question from Christian: Are there any as there are many approaches now to entangle larger and larger particles? How does that may help in the error correction area? I mean, not only having larger atoms, but also maybe pairs of different atoms. Whoa, quite difficult questions. A bit of outside of the scope, but
Uh-huh. So entangling. Yeah, I'm not sure there's a direct connection between research um on entangling. Well, I guess it depends on your platform. So if you're working on superconductors, then the developments that are the most helpful are the ones where you're entangling more and more superconducting qubits. If you're working with neutral atoms, then it's useful to have developments where you're entangling more and more neutral atoms. So so that's kind of generally useful needed for quantum computing, I guess, even more generally than for error correction specifically. Yeah. So
okay.
yeah.
Thanks. There was also a comment from Krzysztof that entanglement purification procedure is a kind of answer to this question. Good. Okay. I do not see more questions on the chat, but maybe someone would like to unmute and ask one more. Okay, we don't have more questions. So, Maria, thank you once again for, first of all, for the great presentation and also answering all these questions. That was really great and really enjoyed. And we also like to thank all the participants for coming today and asking some such interesting questions. Before we leave, if you still have time, I will just share a few last slides just to announce or show you some useful links. Yes, I hope you can see my screen now. So yes, if you are interested in our meetups, let's stay in touch. You can follow our profiles on social media or join our groups, subscribe to our newsletter or YouTube channel. I would like to thank once again our strategic partners for supporting us and our honorary partners as well. And if you like, you can also donate our activities. There is such an option as well. And finally, we'd like to invite you to episode, this will be 65 of our meetup on March 6th. Alex Linden will give a talk. We do not have the exact title yet, but I heard from Alex that she's going to talk about the Google Willow processor, so it can be interesting as well. All right, so we thank you once again for your attention. I will now stop sharing my slides and I will also stop recording. Yeah, there was a comment from Maya that was a wonderful talk. We all agree, so thank you, Maria, once again.
Thanks.